Hello everyone! In the video today, we're going to talk about charts with Riemann sums, mean value theorem, and average rates and average values. So this is a pretty common free response question, about as common as the rate in, rate out ones, and the area and volume questions, and the slope fields one. So it's like 4 or 5 that show up every single time. Alright, let's get to it. The breakdown of the questions. Mostly they talk about Riemann sums. They also ask you to approximate the derivative, and in each of these we have some table of values. They ask about average value, which is different from average rate of change, and they ask about mean value theorem. Then there's like random other questions they ask about, but it was hard to fit those because they're different for each question. Alright. Average value versus average rate of change. This is where it gets tricky because you see the word average and then you do one of them. We have to be careful which one we do. So average value is when they give us the function and ask for the average value of that function. So this is the 1 over b minus a, integral from a to b of f of x. If they ask for the average rate of change, then we need to do slope. So we'll use the table of values or a graph or a function, as long as we can get the two y values or the outputs divided by the two x values or the inputs. And this shows up a lot. Okay, mean value theorem. Before I say anything else, this is basically it. This picture pretty much sums it up. If we have a differentiable function on the interval a to b, then there's some c, doesn't have to be right in the middle, but it's somewhere between a and b, where if we take the tangent line at that point, or the derivative, the slope of that tangent line is equal to the slope of this secant line. You can see they're parallel, and parallel lines have the same slope. So this is very important. We can only use mean value theorem if our function is differentiable. There's a lot of multiple choice questions that ask you if you can apply mean value theorem, and you can only if the function is differentiable. For part 2 questions, before we say by mean value theorem, we first have to say our function is differentiable, therefore we can use mean value theorem. By mean value theorem, blah, blah, blah. So basically it's just saying there is some c in the interval a to b such that f prime of c is equal to f of b minus f of a over b minus a. You should recognize this. It's the formula we just saw, the formula you've seen since 9th grade, the formula for slope, or average rate of change. Another way of thinking of this is that the slope of the tangent line at c is equal to the slope of the secant line between a and b. And then even another way, a third way to think about this, is with derivatives, the instantaneous rate of change is equal to the average rate of change for some value c. And I'm going to put a box around this because the form of this is really important. We definitely need to know this. Derivative at c is equal to average rate of change. Alright, Riemann sums. Just a general overview of all of them and a few examples. Question, what are we doing? What are we doing with Riemann sums? We're approximating the area under a curve with a bunch of rectangles. What's the area of one rectangle? You know that. It's just base times height. So what's the area of a bunch of rectangles? Just add them up. Just add up all of these areas of rectangles. And by the way, this is a picture of a midpoint rule. We know it's midpoint because where the function crosses, where our rectangles cross the function is in the middle of each rectangle. Not on the left or right, but in the middle. So this is an example of midpoint rule. And I wanted to show that this idea of approximation extends to 3 dimensions. This is approximating the volume under this curve in 3 dimensions. Instead of using rectangles, they use rectangular prisms, so they're 3-dimensional. Okay, some quick tips for Riemann sums. With the left Riemann sum, we start with the left endpoint, or the smallest number, and we skip the right endpoint. We just don't include it. With the right Riemann sum, it's the opposite. We start with the right number, or the biggest number, and we skip the left endpoint. With midpoint, it's a little bit trickier. We add delta x over 2 to the left endpoint, and then we add the usual amount each time, and we'll see an example of that. Trapezoidal rule, we need to remember two things. The first one is to divide delta x by 2, and the second is to multiply the meat by 2. And when I say meat, I mean like when you make a sandwich, you have the bread pieces, and then the meat is in the middle. So we're going to multiply all of the heights of the rectangles by 2, except the bread pieces, only the meat. And again, we'll see an example of that soon. So, Riemann sums. We know the area of each rectangle will be base times height, and we're going to use different notation for that. The base, we're going to use delta x, or delta t if they're talking about time, and for the height, it'll be f of x, or in this case, r of t. And if all the bases are equal, they'll say something like equal subdivisions, we can factor out the delta x. And you know the formula b minus a over n. So, an example, use a right Riemann sum to approximate the integral from 0 to 24 of r of t dt using 4 equal subdivisions. This is going to keep notifying me over here. Anyway, right Riemann sum means we start all the way at the bottom. First we'll do delta t, 24 minus 0 over 4. That's b minus a over n, 4. We get 6. So we start at the right, and we stop when we get 4 different intervals, subdivisions. So this is what we write. The integral from 0 to 24 of r of t is approximately, this wavy equal sign means approximately, delta t times the function at 24 plus the function at 18 plus the function at 12 plus the function at 6. And again, these would represent the heights of each rectangle. And all together, we get 255. We use these outputs inside, we add them up, multiply by 6, we get 255. All right, let's use the same table of values, but with left Riemann sum. The only thing that changes is the points we take in our table. Delta t is the same, but since it's left Riemann sum, we start with the left endpoint, or the smaller number. So 0, 6, 12, and 18, we leave off the last one, 24. Oh my gosh, go away things. You don't need to tell me every single email. Okay. So again, the only thing that changed was the endpoint. We're doing the function at 0, the function at 6, at 12, and at 18, leaving out 24. And this is just a coincidence that we get exactly the same number, 255. Okay, what if I said something crazy, like trapezoidal sum? Okay, this is the thing we need to remember. With trapezoids, we're using all of the points. We're not leaving anything out, like with left hand or right hand. We're using everything. And we divide delta t by 2. We multiply the meat pieces by 2. So notice that the two end pieces, which I'll call the bread, they don't get multiplied by 2, but everything else does. Everything on the inside does. That's all you need to remember for trapezoid rule. And yeah, just emphasizing that these in the middle get multiplied by 2. So when you do all the math, you end up with 255. Again, you're not likely to get the same answer for each one. It just happens to work with this data. I think it's like a linear, or it might be an absolute value looking function, which is why we're getting the same answer for everything. But that usually doesn't happen. Okay, sometimes they'll ask us to approximate the derivative with a table of values. And to do this, we'll calculate the average rate of change near the number. So for an example, approximate the value of r prime of 15 and explain the meaning of r prime of 15 with appropriate units. So r of t is a rate, it's gallons per hour. It's probably water being pumped in or water being pumped out of a tank. But anyway, we look at 15, then we look at the 2 points closest to it, 12 and 18, and those are the values we're going to use for the average rate of change. So we're approximating the instantaneous rate of change with the average rate of change. So with these values, we do 10.7 minus 11.4 over 18 minus 12, and we get negative 0.117 gallons per hour squared. And since we're taking the derivative, it's like dividing by time again. That's why we get per hour, or per hour squared. So the explanation. This is the rate at which water flows out of the pipe is decreasing by approximately 0.117 gallons per hour squared at t equals 15. So try to write full sentences with your explanations. We have what's happening. We have the number with correct units and at what time it's happening. Okay, let's jump into the problem. Notice that I stole the table of values from this problem. The rate at which water flows out of a pipe in gallons per hour is given by a differentiable function r of time t. Differentiable, that's important. The table above shows the rate as measured every 3 hours for a 24-hour period. Here's our table. The first question, use a midpoint Riemann sum with 4 subdivisions of equal length to approximate the integral. Using correct units, explain the meaning of your answer in terms of the water flow. Okay, so this is the only one I didn't give an example of because we can just do it in the problem. So, midpoint with 4 subdivisions. First, I'll calculate delta t. We already did it before, but I'll show the work. B minus a over n gives us 6. Then, you don't need to do this step. I'm just doing it to explain thoroughly. Let's put from 0 going up by 6 until we get to 24. Now, we want the middle of all these points. So, think from the hint before, we take delta x divided by 2, that would be 3, and we add it to the left-hand point. So 0 plus 3 is 3. Then to get each next point, we just add 6. 9, 15, 21. These are the points we're going to use in the table. 3, 9, 15, 21. And if you rewind this video to when we were doing left point and right endpoint, we didn't use these values. We only used 0, 6, 12, 18, 24. So another easy way to do midpoint is if you think about left and right, it's the ones in between those that we're going to use for midpoint. Okay, let's put everything together. The integral from 0 to 24 of r of t is approximately delta t, or 6, times all of the outputs of these. So 10.4 plus 11.2 plus 11.3 plus 10.2, and we get 258.6 gallons. So our explanation would be the total amount of water that left the tank, because it's flowing out of a pipe. The total amount of water that left the tank between time 0 and time 24 hours was 258.6 gallons. And we get 3 points for this. 1 for showing the Riemann sum, 1 for the answer, and 1 for the explanation. B. Is there some time t between 0 and 24 such that r prime of t equals 0? Justify your answer. So when they use this language, is there some time where the derivative equals something, that's a huge hint to think about mean value theorem. Is there a time that exists where the derivative equals some specific value? It doesn't have to be 0, just some specific value. And that means think about mean value theorem. So r is differentiable, which means it's continuous. And if that is true, both of those things are true, we can apply mean value theorem. So we're going to write f prime of t, sum time t, is equal to the average rate of change over this interval. So luckily for us, this does work, because if you look at these 2 points, the outputs are the same. We get 9.6 minus 9.6, and that would give us 0. Excuse me. So there is some point t in the interval such that the derivative is 0. And this is their explanation. Yes, since r of 0 equals r of 24, 9.6, the mean value theorem guarantees that there is a time between 0 and 24 such that the derivative at that time is 0. Cool. C. The rate of water flow, r of t, can be approximated by this crazy function. Use q of t to approximate the average rate of water flow during the 24-hour time period. Indicate units of measure. Okay. Something I want to highlight. It's the rate of water flow, and they want the average rate of water flow. So they give us a function for rate of water flow, and we need to find the average rate of water flow. That's average value. All we have to do is 1 over b minus a. 24 minus 0 is 24. Integral of q of t. And if we do that, we'll get 10.785 gallons per hour. Actually, I might have gotten the units wrong there. Because this is gallons per hour, so I think this should be... No, this should be good. Gallons per hour is correct. That makes sense. All right. Well, hold on a second. We get 3 points for this. 1 for the limits and average value constant. That's the 1 over 24. 1 for the integrand, and 1 for the answer. All right, not so bad. Only 3 parts. High five someone. Zoe's not here, so I'll high five myself. This is how giraffes high five. Okay, another one. This is also a good review of some of the ideas of particle motion. So the graph of the velocity v of t in feet per second of a car traveling on a straight road between 0 and 50 is shown above. A table of values for the velocity at 5-second intervals of time is shown to the right of the graph. Part A. During what intervals of time is the acceleration of the car positive? And give a reason for your answer. So, what does it mean that the acceleration is positive? Well, whenever you think of particle motion, always think, what is the function you start with? What is the function you want to know about? We start with velocity. We want to know about acceleration. How do we go from velocity to acceleration? We look at derivatives or slopes. So, during what intervals of the time is the derivative positive? Well, if the derivative is positive, it means the original function is increasing. So the acceleration is positive on the interval 0 to 35 and 45 to 50, because that's where the velocity is increasing. We get 3 points for that. 3 points for that. Just to say where the acceleration is the positive, if we make the connection that that's the derivative of velocity, and if it's positive, it means the velocity is increasing. And we show the two intervals, 0 to 35 and 45 to 50. Then we get 3 points. That's a pretty quick 3 points. All right, what's next? Part B. Find the average acceleration of the car in feet per second squared over the interval 0 to 50. Okay, so again, they're not asking for the average velocity. Then we would do the 1 over b minus a thing. They're asking for average acceleration, which is like one step above. It would be the slope, or the average rate of change for velocity. So what do? We take these 2 points, 0, 0, and 50, 72, and we use our average rate of change formula. And we can just leave it as this, 72 over 50 feet per second squared. And we get 1 point for the answer. I'm okay with that. It's pretty quick. C. Find one approximation for the acceleration of the car in feet per second squared at time 40. Show the computations you used to arrive at your answer. Okay. Remember, again, that acceleration is the derivative of velocity, so we're approximating the derivative at 40. We did an example of this before. So, here is t equals 40. We're going to use 2 points close to it to approximate it and plug those in. So, 60 minus 81 over 45 minus 35, we get negative 21 over 10 feet per second squared. And we get 2 points for this, 1 for the method, 1 for the answer. And there's a bunch of methods, but I like this one the best because it's like the quickest. And these are all the different ways they did it. We can use a bunch of points as long as they're close to 40. So they use 45 and 40, 40 and 35. I prefer using the 2 points, 45 and 35, but all of these points are acceptable. Part D. Approximate the integral from 0 to 50 of v of t dt with a Riemann sum using the midpoints of 5 subintervals of equal length. Using correct units, explain the meaning of this integral. Okay, this is probably a 3-point question, I'd guess, since we need to do a Riemann sum and we need to use correct units. I could be wrong, but we got to explain it. So midpoints. First, delta t is 10. That one's easy. b minus a over n, 5. And this is what we can do. Did I highlight them? Okay, I did. So starting from 0, going by 10, these are all the original points, but then we use the ones in the middle, because it's midpoint. Just use the middle ones. So if we plug in all of these, we get 12 plus 30 plus 70 plus 81 plus 60, which we wrote here. We multiply that by delta t. We will get 2530. And I left off units. Whoops. But it gives the displacement of the car from 0 seconds to 50 seconds. I forgot my units here, so I should put them in. Should be feet? Yes, feet. And it gives displacement and not distance because there's no absolute value. Technically, I think it could be the same because it's not going below the t-axis, but we don't need to worry about that. Just saying displacement is correct. And it was 3 points. One for the sum, Riemann sum, one for the answer, and one for the meaning of the integral, that it gives the displacement between 0 and 50 seconds. And I probably should include the number here too. So I should say the displacement of the car from 0 to 50 seconds is 2530 feet. All right, another one done. Go crazy. Like this baby elephant. That's adorable. I love it. He's just having the time of his life. All right. Last one. The temperature in degrees Celsius of the water in a pond is a differentiable function W of time t. The table above shows the water temperature as recorded every 3 days over a 15-day period. Blah, blah, blah. Use data from the table to find an approximation for W prime of 12. Show the computations that lead to your answers indicate units of measure. Okay, I like these problems. Approximation for W prime. Easy peasy, we got this. Okay, so we're going to use these 2 points. There's 12. We can use 9 and 15 in our computations to find the derivative near that. So using 21 minus 24 over 15 minus 9. Made a mistake there. That's supposed to be 6. But the answer is the same in the end. Negative 1 over 3 degrees Celsius per day. Remember, when we take the derivative, we're dividing by whatever unit they're using for time. So it's degrees per day. Also, the units on top are degrees. The units on bottom are days. We don't have to be as crazy as we are in physics with including them in the computations, but we need them in the end. And we get 1 for the difference quotient. That's what this thing is called. And 1 for the answer with units. If we don't use units, we get no points, which is a bummer. But that's okay, you'll remember units. Part B. Approximate the average temperature in degrees Celsius of the water over the time interval 0 to 15 days by using a trapezoidal approximation with subintervals of length 3 days. Okay, a lot going on here. They're asking for the average temperature, and the function we give is temperature. So we're going to do average value, 1 over b minus a integral from a to b of the function, w of t, but instead of the integral part, we'll just do the Riemann sum, the trapezoidal sum. So we'll do this in parts. First, we'll find the trapezoidal sum. Then we will multiply that by 1 over b minus a to get the average, temperature. So delta t is 3. They give it to us. And here we go. 3 divided by 2, divide by 2 because it's trapezoidal. And then we use all of these points, 0, 3, 6, 9, 12, 15. We use all of the outputs. They all show up, but everything gets multiplied by 2 except the bread pieces. Bread pieces don't get multiplied by 2, everything else does. When we do this calculation, we get 376.5. And I left off the units. I shouldn't have, but I did. What are the units? It should be degrees Celsius. So the average temperature, we just divide by 15, because 15 minus 0 is 15. And we get 25.1 degrees Celsius. So we get 1 for the trapezoidal method, showing this work, and 1 for the answer. I'm assuming units count here too. Okay, C. A student proposes the function p given by blah 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 as a model for the temperature of the water in the pond at time t, where t is measured in days and p of t is measured in degrees Celsius. Find p prime of 12. Using appropriate units, explain the meaning of your answer in terms of water temperature. Okay, so other than the explanation and everything, this all boils down to this little part here. Find p prime of 12. Well, they give us the function, so let's use the calculator to find the derivative and plug in 12. So use the calculator. Math 8. Let's put in x there because it's the derivative with respect to x. We won't put t. Then we'll just write the function exactly as we see it, but with x's instead of t's. And then over here, we have our little line that says evaluate at x equals whatever we want. We'll put in 12 here. And when we're all done, what do we get? Let's see, negative 0.549. And we'll write that degrees Celsius per day. The same units as we had in part A, I think. Degrees Celsius per day. So the explanation is that the temperature is decreasing at a rate of 0.549 degrees Celsius per day at t equals 12 days. And again, notice that when we say decreasing, we don't include the negative here, even though we had a negative in our answer. If we said decreasing with a negative, it really means increasing, kind of like a negative times a negative is a positive. For this, we get 2 points. One for p prime of 12, with or without units. Ooh, we don't even need units there. Awesome. And one for the interpretation. Nice. Okay, last part. Use the function p defined in part C to find the average value in degrees Celsius of p of t over the time interval 0 to 15. This is beautiful. It's just average value. And they give us the time interval. We already have the function p. So we do 1 over 15, integral from 0 to 15 of p of t, and we get 25.757 degrees Celsius. They don't even tell us to explain anything. Awesome. And this is 3 points? What? That's nuts. 1 for the integrand, 1 for the limits and average value constant, and 1 for the answer. So some of the questions here might have been pretty tough, but I feel pretty good about this part D. 3 points for average value. I'll take it. All right. We did 3 problems. Be like this cat and take a break. I'll see you in the next video.